Hi there, this is Dr. McFerrin with DM Explains. In this video, I'm going to go through a series of 4 different examples looking at analyzing and designing MOSFET amplifiers. So let's start with example 1. In example 1, I would like you to design the voltage divider bias circuit for a common source amplifier where VTN is 1 volts, Kn is Kn prime times width over length, that's 4 milliamps per volt squared, and the early voltage VA is 100 volts. Design this for ID equal to 0.5 milliamps, a source voltage VS of 3.5 volts, a drain voltage VD of 6 volts. If my DC voltage source is 15 volts, I'd like you to specify RG1 and RG2 to get a current of 2 microamps in the voltage divider. And then I would like you to also give GM and R0 at that bias point. In order to solve this problem, I need to remember that ID can be found by taking VDD minus VD over RD. I have values for most of these things. I know that ID is 0.5 milliamps, and I know VDD is 15 volts, and V drain is 6 volts. And so RD is going to equal to 15 minus 6 over 0.5 mil, which is 18 kiloohms. Next, I know that Vs over Rs also has to be equal to ID, which means that Rs is equal to Vs over ID, which is equal to 3.5 over 0.5 milliamps, which is equal to 7 kiloohms. I also know that ID is equal to 1/2 Kn V overdrive squared. So we can solve this for V overdrive. V overdrive is equal to the square root of ID times 2 divided by Kn, which is equal to the square root of 0.5 mil times 2 over 4 mil. That's equal to 0.5 volts. I also know that V gate to source is VTN plus V overdrive, which is equal to 1 plus 0.5, so this is 1.5 volts. So V gate is equal to V gate to source plus V source, which is equal to 1.5 plus the source voltage, which is 3.5, so this should be 5 volts, which means that V gate is 1/3 of VDD. I know for the voltage divider that R gate 1 plus R gate 2 times my current in that voltage divider, which is 2 microamps, has to be equal to the source voltage 15 volts. And so that means that R gate 1 plus R gate 2 is equal to 7.5 mega ohms. Now I also know that since V gate is 1/3 VDD, that means that R gate 2 over R gate 1 plus R gate 2 is equal to 1/3, which is equal to R gate 2 over 7.5 mega ohms. That means that R gate 2 is equal to 7.5 meg divided by 3, so R gate 2 is equal to 2.5 mega ohms. We can then solve for R gate 1. It's equal to 7.5 mega ohms, the sum of R gate 1 plus R gate 2 minus R gate 2, which is 2.5, so this should be 5 mega ohms. So far what I've found is RD, RS, R gate 1 and R gate 2. Those are the things I need to bias, and then the other part of the question asked me to find GM and R0. GM is 2 times ID over V overdrive, which is equal to 2 times 0.5 mil over 0.5, which is equal to 2 milliamps per volt. The last part is little r naught, which is the early voltage divided by the drain current, which is 100 over 0.5 mil, so 200 kiloohms. On from this example, we can move to example 2. In this example, I ask you, okay, based on the design in example number 1, find the input resistance Rn, the output resistance R naught, and the overall voltage gain from the signal source to the output with a load attached for a common source amplifier if R sig is 100 kiloohms and RL is 2 kiloohms. To solve this, I need my small signal model. So let's go ahead and draw that. I've got V sig on the left over here and R sig in series with this. That's 100K based on the problem statement. And based on the design above, I had R gate 1 and R gate 2 as 5 meg and 2.5 meg, and I measure across that V gate to source, and I've got a dependent current source, which is GM V gate to source, so that is 2 mil times V gate to source. Across there I have my R naught, which I found to be 200 kiloohms. I also found my drain resistor to be 18K, and then I'm going to attach a load to that. Let me correct my example, it's supposed to be 20K at the load, so the load is 20K, and there's where I find V naught. So I'm looking for the input resistance. The input resistance is found by looking at those input terminals and taking the combination of the resistors there. So Rn is going to be 5 meg in parallel with 2.5 meg. That's 1.67 mega ohms, which is a very nice large resistance. R naught is found by looking without the load resistance attached back through the output terminals. So R naught is found there. R naught then is 200K in parallel with 18K, which is equal to 16.5 K ohms, just about. GV is equal to the output voltage V naught over the input voltage V sig, which is the same as VGS over V sig multiplied by V naught over VGS. So this is equal to R input over R input plus R sig multiplied by negative GM R naught in parallel with RD in parallel with RL, which is equal to 1.67 meg over 1.67 meg plus 100K multiplied by negative 2 mil times 200K in parallel with 18K. I already found that to be 16.5K in parallel with 20K. And when I calculate this out, I get that GB is negative 17.1 volts per volt. You can check that on your own, but that is the gain with the signal source and a load resistor of 20 kiloohms for this system. In example 3, I have a much more robust question. What I'd like to do is I'd like to find an amplifier design for a desired value of V overdrive equal to 1 volt. This MOSFET has Kn equal to 2 milliamps per volt squared, an early voltage of 100 volts, and a turn-on voltage VTN of 0.5 volts. I'd like to find the resulting ID and then design the bias circuit to realize this for a voltage divider biased common source amplifier. We desire less than 10% signal loss across R sig. I'll tell you what R sig is in a moment. I've got a DC voltage source of 12 volts, and I want you to calculate the input resistance, output resistance, and overall voltage gain if the signal source has a 10 kiloohm resistance and the load is a 10 kiloohm resistance. To solve this, I first must find ID. ID is 1/2 Kn V overdrive squared, which is equal to 1/2 times 2 mil times 1 squared. So ID needs to be 1 milliamp. A common rule of thumb for designing an amplifier is to try to evenly split the DC voltage across the drain resistance, source resistance, and MOSFET itself. So for the rule of thumb, let's split VDD into thirds. So that means that V drain should be equal to 8 and V source should be equal to 4 volts. So my bias circuit will look like this. I've got my voltage divider over here, R gate 1, R gate 2. Then I've got my MOSFET, and then over here I have my drain resistance RD and my source resistance RS. And I know that VD is going to be 8 volts and VS is going to be 4 volts, VDD being 12 volts up here. So just like I did in example number 1, I know VDD minus VD over RD has to equal to ID, which implies that RD is 12 minus 8 over 1 mil, or 4 kilo ohms. To find the source resistance, I take VS minus 0 over RS. This is equal to ID. This implies that RS is equal to 4 over 1 mil, or also 4 kilo ohms. So that's not too bad. The next thing I know is that V gate is equal to V gate to source plus VS. To get V gate to source, I'm going to take my overdrive voltage plus VTN, which is 1 plus 0.5, or 1.5 volts. And so V gate is equal to 4 plus 1.5, or 5.5 volts. That means that V gate needs to be 5.5 over 12 VDD, because VDD is 12, so that's how I get 5.5 volts. Or in other words, it's 0.4583 VDD, which means R gate 2 over R gate 2 plus R gate 1 is equal to 0.4583. We can solve this, so I know that R gate 2 minus 0.4583 R gate 2 is equal to 0.4583 R gate 1, or in other words, R gate 2 is equal to 0.8462 R gate 1. Now I know that R sig is equal to 10K, and to avoid a signal loss of more than 10%, if I draw this little voltage divider, this is R gate 1 in parallel with R gate 2, and this is 10K. I want to avoid a signal loss greater than 10%, so 90% of the signal needs to make it across R gate 1 in parallel with R gate 2. That means that if I take 90K, that means that the voltage across R sig is 10K over 10K plus R gate 1, R gate 2. And so that means R gate 1, R gate 2, which I want to be less than or equal to 0.1. I need this to be greater than or equal to 90K. So as long as I choose large values of R gate 1 and R gate 2, that should work fine. So R gate 1 equal to 1 mega ohm should be adequate, because I know that R gate 2 is 0.8462 times R gate 1, which is equal to 846 kilo ohms, and the parallel combination of these two, R gate 1 in parallel with R gate 2, is equal to 458 k ohms, which is sure bigger than or equal to 90k. So I've now designed my voltage divider part. Let's go to the small signal model, redrawing as normal. So I've got V sig, I've got my 10k R sig, I've got a 1 meg in parallel with a 846k. I measure V gate to source across here. And I've got GM V gate to source as my dependent current source. Little r naught is equal to VA over ID. That's equal to 100 over 1 milli, which is 100k. So I've got 100k as little r naught. That's in parallel with the value for RD I found, which is 4 kilo ohms. And then I put my load resistance across there, which I said was 10k, and then I measure V out across there. GM is calculated by taking 2ID over V overdrive, which is equal to 2 times 1 mil over 1, or 2 milliamps per volt. I asked you for R input as well as R output. Let's start with R input. R input is seen looking into the input terminals here, and it's 1 meg in parallel with 846k, which I already told you was 458 kilo ohms. R naught is the resistance as I look back through the output terminals with the load resistance removed. So that's equal to 100k in parallel with 4k, which is approximately 4k. It's actually equal to 3.85k ohms. And then the last part I ask you for is GV. GV is found by taking the stuff on the input, which is 458k over 458k plus 10k, and multiplying that by negative GM. This comes from the output part. So negative GM, which I just said is negative 2 mil, multiplied by the parallel combination of little r naught, RD, and RL, which is 3.85k in parallel with 10k. And when we plug this into our calculators and get it, it's negative 5.44 volts per volt. Notice that this is actually quite a small gain, mainly because the load resistor is relatively small. In my last example, what I would like to do is take the design from example 3 and look at what would happen if I had to choose a standard 5% resistor values. How would this change the results? So let's look for closest values. The closest for RD and RS, which were originally 4K, is 3.9 kilo ohm. In this case, ID is VDD minus VD over RD, which is supposed to be 4 over 3.9. And so I get 1.03 milliamps, which is close enough to ID for what we want. Now the closest for RG1 and RG2 is 1 mega ohm, which fortunately is what we calculated for RG1, and either 820k or 1 mega ohm. If we choose 1 mega ohm, then V gate becomes 6 volts and V gate to source is 2 volts. The overdrive voltage is 2 minus 0.5 or 1.5 volts. So that's a significant change to my overdrive voltage. If RG2 is 820k, then VG would be equal to 5.41 volts, and V gate to source is equal to 1.41 volts, and so V overdrive is going to equal to 1.41 minus 0.5, which is 0.91 volts. That is much closer to the desired 1 volt than what happens if I choose the 1 mega ohm, so we're going to choose our gate 2 equal to 820 kiloohms. And so what I'd like to do is calculate what the actual value of ID would be. It's 1/2 times 2 mil times 0.91 squared, which is 0.828 milliamps. So the real value of VD is going to be 12 minus 0.828 times 3.9. That's 8.77 volts. And the real VS is 0.828 times 3.9. That's equal to 3.23 volts. So I can see how this has changed what the original design looks like. Now let's go to the small signal model. I've got V sig here. I've got my nice 10K right here. I've got a 1 meg in parallel with a 820K. Across there is where I measure V gate to source. Then I've got my values here. We'll see how GM and R0 are changed, but this is GM, VGS. And I've got an R0 here, and I've got a 3.9 here, and then a 10K load resistance, V0. So the input resistance is 1 meg in parallel with 820K, which is equal to 450 kiloohms. Comparing that to what we had before, that is slightly smaller. The value for little r0 is 100 over 0.828 mil, which is 120 kiloohms. That's bigger than it was before. GM is 2 times 0.828 divided by 0.91. That's 2 ID over V overdrive. That's equal to 1.82 milliamps per volt, so I expect that to be smaller than I was before. The output resistance R0 is going to be little r0 in parallel with 3.9K. My RD, that's equal to 120K in parallel with 3.9K, which is 3.78 kiloohms, which has also decreased slightly from what I had in my original design. GV is going to equal to RN, which was 450K over 450K plus 10K times negative 1.82 times 3.78 in parallel with 10K. When I multiply all this together, I get negative 4.88 volts per volt, which has decreased the gain from example 3. So what I notice about using the 5% realizable resistors is that I have decreased my input resistance, decreased my output resistance, and thereby decreased my overall system gain. Hopefully these examples have helped you put amplifier design and analysis into perspective. I hope you found this useful. As always, thanks for watching. We'll see you next time.